Good afternoon and welcome. My name is Stephen Hubbard and I am the interim head of the Department of Geoscience in the Faculty of Science. It's wonderful to have so many faculty, students, alumni, and other community members connecting with us virtually today for this year's Tom Oliver Lecture. I hope many of you were able to take in our geoscience research event earlier this afternoon. Normally, we enjoy having our community interact around posters from department members outside the Tom Oliver Lecture Theater on the first floor of the Earth Sciences building. Although that wasn't possible today, we had an extremely successful online research symposium in its place. Very special thanks to Dr. Rajiv Nair for driving this important initiative, helping to ensure we find time for scientific discussion during these strange times. If you did miss the session, note that we will post all presentations on our departmental website later this month. Also of note, we are recording today's session and will be posting the video on the Faculty of Science website. I encourage you to check out our website at science.ucalgary.ca for the video and for other Faculty of Science events. In these times of physical distancing and virtual connections, I like to think about who I'm sharing this space with now, both far and near. We are broadcasting from Calgary, which is located on the traditional territories of the people of the Treaty 7 region in southern Alberta, which includes the Blackfoot Confederacy, comprising the Siksika, the Piikani, and Kainai First Nations, as well as the Tsuut'ina First Nation and the Stoney Nakoda, including the Chiniki, Bearpaw, and Wesley First Nations. The city of Calgary is also home to Métis Nation of Alberta, Region 3. The Tom Oliver Lecture is named in memory of Dr. Tom Oliver, who not only founded the Department of Geology in 1959, but was also the inaugural department head until 1965. In 1978, Dr. Oliver became the Dean of the Faculty of Science. Under his leadership as Dean, Tom was instrumental in championing and developing the geophysics program, and he oversaw the dramatic growth of the department in the late 1970s. Today, we continue to celebrate and honor Dr. Tom Oliver, his leadership, and his legacy through the annual Tom Oliver Lecture. We gratefully acknowledge Tom's family and the many friends of Tom who made this series a reality through their support. In particular today, I would like to extend a warm welcome to Tom's wife, Margaret, and their children, Mark, Jane, George, and Jim, as well as George's wife, Marla, who are joining us online today from all across the country. We are so glad you are part of this year's virtual lecture. This annual lecture continues to share and promote science leadership, research, and excellence. The event has become an invaluable opportunity to engage with our science community and for our science community to engage with us. Now, before we get to our main event, I'd like to take just a few minutes to acknowledge some exceptional members of our geoscience community. When the pandemic began here in March, many of our regular tasks got put to the back burner as everyone directed all their efforts into delivering classes virtually. During this time, we missed recognizing outstanding accomplishments by our faculty and staff during the 2019-2020 academic year. At a time when our entire department deserves kudos for working harder than ever, I'd like to recognize 5 individuals. Our Departmental Research Excellence Award is earned by Dr. Jan Detmer. Jan is a highly collaborative scientist whose diverse research interests include seismology and acoustics. Recent success includes being the only researcher in the Faculty of Science to be successful in the initial round of the National New Frontiers in Research Fund. Dr. Glenn Dolphin is recognized with the Teaching Excellence Award. Glenn holds the Tamrat Chair in our department. As a geoscience educator, Glenn's novel contributions include adapting teaching concepts using the history and philosophy of science, exploring the influence that scientific and teaching metaphors have on student learning, and investigating how students learn from interacting with virtual outcrop models. Our Service Excellence Award is earned by Dr. Rachel Lauer, who has been active serving at all levels. Currently, Rachel co-chairs our Department Equity, Diversity, and Inclusion Committee, as well as our Modernize the Curriculum Committee. She serves as a member of the University General Faculty's Council and also sits on the University Senate. Despite being relatively new as a faculty member, Rachel has been making an immense positive impact on the university community. Our Research Staff Award is given to Celia Kennedy. Celia is the program manager for the Create, Redevelop initiative. This program for enhanced graduate training focuses on responsible development of energy resources and development of future leaders in industry, government, and academia who bring deep knowledge and appreciation of indigenous ways of knowing, along with cross-disciplinary skills in science and policy. Celia's leadership has ensured success of this important initiative. Lastly, not leastly, we recognize Lynn Maillet with our Departmental Staff Award. Lynn has given many years of service as Department Technical Manager before taking up her current role this year with the Faculty of Science. She worked tirelessly for our department over the years, going above and beyond her role with the best interests of our campus community at heart. Congratulations to Jan, Glenn, Rachel, Celia, and Lynn. I'd like to thank the Department Awards Committee led by Dr. Dave Eaton for ensuring we recognize these outstanding contributors to our department during these challenging times. Now, without further ado, the reason we're all here, I would like to welcome Dr. Ben Tudelo, who will introduce today's speaker. Ben is an assistant professor in the department who specializes in aqueous geochemistry and reactive transport processes throughout the Earth's crust. Ben has been involved with the Tom Oliver Lecture for a number of years, and through his leadership, this event continues to attract internationally renowned researchers who are willing and ready to discuss and share their current research and perspectives with our community. Welcome, Ben.
Thank you, Steve. It's my great pleasure to be here today and to be part of this year's Tom Oliver Lecture, virtual Tom Oliver Lecture. I'm so happy to see so many of you turn out to hear today's lecture. The attendance is fantastic. Our speaker today is Dr. Peter Kelvin. Peter is the Arthur D. Storke Professor in Columbia University's Department of Earth and Environmental Sciences, based at Lamont Doherty Earth Observatory. He's a member of the United States Academy of Sciences, a fellow of the American Geophysical Union, the Mineralogical Society of America, and the Geochemical Society, and a recipient of the American Geophysical Union Bowen Award. His research focuses on chemical and physical feedbacks during reactive porous flow of fluids and associated deformation. I personally first came into contact with Peter when he gave a talk about carbon mineralization at the University of Minnesota early on in my PhD studies. Peter's presentation that day was absolutely magnetic. It was very provocative, and it ultimately changed the direction of my research. I've now attended many of Peter's presentations over the intervening time, and I know that magnetic, exciting, compelling quality pervades all of them. I'm therefore very excited to welcome you to this talk titled Carbon Mineralization for CO2 Removal from Air and Permanent Storage that he has in store for all of us today. It is my pleasure to welcome Dr. Peter Kelvin.
Thanks very much, Ben, for that really kind invitation or introduction. And I'm going to quickly switch on my screen here and get going because, as Ben knows but didn't tell you, I am notorious for showing too many slides. So please view this as a slow movie and not a fast slideshow. And know that I will be happy to send you all these slides on request. And I guess also it sounds like the recording of this talk will be online. And so you can play it back slowly if you want to. So I'm going to talk about carbon mineralization for CO2 removal from air mainly, but also permanent storage today. And if I listed all the people that are co-authors on this talk, it would take up the whole slide. And so in the interest of time, I haven't done so, but be aware that this is the result of many, many people's work. I'm going to start with some philosophy, and so bear with me. And so this is the, I think, first figure in the recent National Academy report on CO2 removal from air and reliable storage in 2019, which is a PDF that you can download for free from the National Academy's website. So what it's showing you is that, currently or soon, we will be emitting something on the order of 50 billion tons of CO2 equivalent. And that in order to achieve the target of keeping global warming below 2 degrees C, the IPCC and the UN and other authoritative organizations have realized that even with the best abatement efforts possible, we probably will remain with about 20 billion tons of CO2 equivalent emissions, mostly methane, but also hard to control distributed emissions of CO2 by the end of the century. Whereas to stay below 2 degrees C of warming, they project that we have to have net zero emissions by about 2090. So how can that be done? And so they've kind of concluded that we need to have on the order of about 10 billion tons of CO2 removal from air in one way or another by mid-century and about 20 billion tons of negative emissions by the end of the century. Okay, so we have to somehow avoid or offset 50 billion tons of CO2 emissions, and much of that might be negative emissions. What is this worth and to who is an interesting question. And I don't want to go through every single number on this slide, but CO2 offsets are currently trading at about $25 per ton in the EU. As you all probably know, there's a carbon tax of $40 per ton in British Columbia, and the Canadian national government has announced a target of a $50 per ton carbon tax, although the time at which that's going to be implemented is a little flexible. The California Low Carbon Fuel Standard, currently CO2 offsets are trading at almost $200 a ton, although that will come down as they approve more people to enter that market, and so on. So one thing that I really like was the Obama administration put together an intergovernmental task force to try to evaluate the damage due to CO2 emissions, described in terms of the social cost of carbon in dollars, in this case, 2007 dollars per ton of CO2 emitted. And I like this illustration of their results because they show that, you know, it's a probabilistic thing. There's not one specific damage. We don't really know what the effect on agricultural production of warming will be, for example. And so they have these different histograms of the probabilities of different outcomes for different growth rates of the economy, 5%, 3%, and 2.5%. As an aside, I should mention that the Interagency Working Group of the Obama administration published their last report in 2016. And in 2017, President Trump disbanded that interagency working group, and the EPA slashed the social cost of carbon value to between $1 and $6 per ton. A recent Yale report says that the social cost of carbon should be $100 to $200 per ton, increasing to nearly $600 by the end of the century. But let's go back to this, which you can get online. So here's the White House report. And of course, you know, this is all cool and it's great to emphasize the fact that we're not certain. And so there's probability distributions. But of course, right away, everybody wants to know, boom, okay. The economy has been growing at about 3% per year for the last several decades. And so, and we can't deal with all this uncertainty. So let's just pick the average value of $40 per ton. Now you'll note that it's not at the peak value here. It's not the most probable value, it's the average, because there's this so-called fat tail on this asymmetric probability distribution. So actually what you'll see is, if you look closely, and I would really prefer if they had used a logarithmic scale on this diagram, what you'll see is that there's a finite probability of higher damages due to a ton of carbon going off the right-hand end of that diagram. So what's over there? What's over there is very improbable but extremely damaging scenarios where the outcome is almost incalculably damaging. And so kind of as a joke, I say, okay, so these folks evaluated this meteorite was, you know, had a 3% chance of hitting the Earth. And they did a bunch of probabilistic cost benefit analyses and decided that they needed to spend $42 per ton of meteorite on rockets. Well, you know, their probabilities were right, but this is an improbable event. So just in a conference one time, there are good papers by real economists on fat tails on the social cost of carbon, but I'm not a real economist and this is not a good paper. But I just sort of amused myself for a few hours by putting a fat tail on that probability distribution. So I digitized the 3% probabilities here. That's that. And then I just said, okay, there's this low probability going out and out and out. And then there's this final event that has extremely low probability, but a very, very large cost. And so that's when everybody dies. So this is the last ton of carbon that was added to the atmosphere before some tipping point was reached. And I decided that dollars don't have much meaning unless there's someone around. So there's two survivors. Oops. Here they are with their refrigerator with beer and their windmill. But 10 billion people just died. And I valued people at $1 million per person based on what the average United States citizen spends on healthcare during their lifetime. So you come up with this enormous social cost of carbon at $100,000 per ton. And you recalculate the average with this fat tail, this low probability, but extremely damaging event. And it comes out to $600 a ton, whereas without the tail, it was $42 a ton. So I just introduced this with the idea that I don't know the answer to this question, but that it could be worth spending quite a lot to avoid a climate catastrophe. And we really don't know how much it's worth. So you can go through all the metrics that you like, but in the end, it's kind of a philosophical decision. All right, so let's get to the geology. So I'm gonna talk about natural weathering of tectonically exposed mantle peridotite with a focus on carbon, of course. And then some ideas about engineered systems. Then we're gonna talk a little bit about some basic science, so-called reaction-driven cracking, loop back to engineered systems, and then finally get to CO2 removal from air. Okay, so let's do the geology first. There are places on the planet, including quite a few in your neighbor British Columbia, where mantle peridotites full of olivine have been thrust toward the surface by plate tectonics and exposed by faulting and erosion. And of course, there are other places, although I'm not going to dwell on it, where mantle-derived magmas come to the surface of the Earth. And in both cases, they're very, very far from equilibrium with the atmosphere and the surface ocean. And so these constitute giant reservoirs of chemical potential energy. These rocks weather very quickly because they're so far from equilibrium with surface conditions. And basically what we aim to do here is to take advantage of that chemical potential energy in order to reduce the cost of CO2 or greenhouse gas mitigation. So this illustration just shows that the free energy is such that the carbonate minerals are the ground state for CO2 at the surface of the Earth in most geologically relevant chemical systems. So all roads lead to carbonate as the lowest energy state, and we can take advantage of those spontaneous exothermic reactions potentially to reduce the cost of engineered CO2 management. Just as in the case of carbon mineralization, what we have in mind is we're going to take magnesium or calcium bearing minerals. We're going to react them with CO2 from air or surface waters, and we're going to make carbonate minerals, magnesite, calcite, so on, which are essentially permanent, inert, non-toxic materials that won't move around on a human timescale. So it's permanent storage as well as CO2 removal from air. The example we always emphasize is olivine from the Earth's interior, 80-some-odd% of the Earth's upper mantle, magnesium silicate, some iron I'm not showing here, reacts with CO2 to form magnesium carbonate, magnesite plus quartz. And you know, this stuff, you can eat it. It wouldn't do you any good, but it wouldn't hurt you. So permanent, non-toxic, inert materials. This reaction is pretty fast at high temperatures. Some basaltic glasses, amorphous basaltic material, reacts about as fast as olivine with CO2 at high temperature, but plagioclase feldspar and therefore crystalline basaltic rocks are quite a bit slower than this at high temperature. We're also going to kind of glance at some products of hydrosalteration of olivine. So when mantle rocks come to the surface, They hydrate to form serpentine and sometimes brucite. The serpentine carbonation reaction is actually pretty slow, but the brucite, the magnesium hydroxide carbonation reaction, is very fast. It's probably faster than olivine, and especially it's faster than olivine at ambient weathering conditions. It's certainly faster than olivine at ambient weathering conditions near the Earth's surface. Okay, so I'm going to show you some cool pictures of carbonate uptake or carbon uptake during weathering of mantle peridotite. But first, let me sort of give you the framework. So rain falls on subaerial peridotites, or seawater on the seafloor reacts with tectonically exposed peridotite on the seafloor. And that leads to an increase in dissolved magnesium here on the right-hand axis, which is charge balanced by uptake of CO2 from air or water to make bicarbonate. So the weathering of peridotite on the seafloor or on the land surface forms what we call type 1 fluids, which are enriched by a factor of 10 to 100 in magnesium and bicarbonate ion. Then some of the water in peridotite formations goes deeper below the surface and loses contact with the atmosphere and continues to react with the peridotite. And along that reaction path, there is precipitation of magnesium carbonate minerals plus serpentine, which drives the dissolved magnesium and dissolved carbon concentrations down to essentially zero. It used to be zero. Now we're very sophisticated and we can measure it, but it's nearly nothing. So that process, in addition to forming serpentine minerals, forms these carbonate veins that you see in these outcrops of mantle peridotite, more or less hydrated or serpentinized mantle peridotite in the Sultanate of Oman, where the world's largest block of mantle peridotite is exposed on land. Then there's lots of carbon precipitation to form those veins, but calcium remains pretty much insoluble. So the small amounts of calcium in peridotite end up forming very, very calcium-rich calcium hydroxide solutions with a pH of almost 12 or sometimes reaching 12. And then this calcium, in some places at alkaline springs, this calcium hydroxide rich water comes to the surface and draws down CO2 directly from air to form travertine deposits. So here's this alkaline spring water, no magnesium, no carbon, pH of 12, lots and lots of dissolved calcium. And it actually pulls CO2 right out of the air to make these big travertine deposits. If you've ever been to Mammoth Hot Springs or the geysers in Iceland, those big travertines formed by precipitation of carbonate minerals from cooling water. Well, they're similar in size. They look kind of similar, but this is basically an isothermal process. So this carbon-free calcium hydroxide rich water is coming to the surface. So here's where the water table intersects the outcrop surface here. And these things that look like ice on the tops of these rim pools, that's actually calcite. And it's supported by surface tension, but when it rains or when somebody comes along and throws a rock in these pools, the little calcium carbonate skim on the surface sinks to the bottom and forms a new layer on these growing travertine deposits. This is just to say that, the schematic diagram I've been showing you is not a lie. So here we see this strongly carbonated magnesium and dissolved inorganic carbon in the fluids going up to form type 1 water and then down again to form type 2 water. And this is the trend I've been showing you on schematic plots, where that type 1 water in the subsurface precipitates serpentine and magnesium carbonate minerals to form the type 2 floats. There's lots of important details in here. And a guy named James Leong is writing really, really super papers about this right now, but that's the schematic sort of starting level understanding. When I first heard people saying, well, maybe we can use olivine to take CO2 out of the air. I was interested. And so on a field trip in the Sultanate of Oman in 2007, we were driving around and I would just leap out of the truck every time I saw some carbonate veins or something and pick them up and throw them in a bag. And we sent those to the Carbon-14, the accelerator mass spectrometer facility at Woods Hole Oceanographic Institution. And, you know, somewhat to my surprise, the travertines are young, okay, that's obvious. But the veins that I showed you in those outcrops that particular year, all but 2 of our samples contained live carbon-14. As if you interpret that in terms of an age, the carbonates in those veins were almost all less than 50,000 years old. So it's an interesting little factoid. And do we think that the process of vein formation just started 50,000 years ago? No, we don't. So the best way I know to interpret these data is that this is kind of a residence time. These veins are forming mostly in a weathering horizon that might extend 15 to 25 kilometers into the subsurface. And then uplift and erosion are removing those veins roughly at a steady state. So they have a residence time on average of about 25,000 years. We can also use these data, and we can go along with tape measures on outcrops, and we can do all kinds of things like that to figure out what the vein abundance is in the subsurface and ultimately derive fluxes based on this average residence time. And we get on the order of 1 million kilograms per cubic kilometer per year of CO2 uptake, or that's 1,000 tons. And then, okay, that's a little hard to get your head around. A cubic kilometer rock, it's pretty big. So that's a gram per cubic meter per year. Then there's some nice lab data. It's been supplemented recently, but it stems from DOE studies at the beginning of this century. And they studied the effect of temperature and CO2 partial pressure on the rate of olivine conversion to magnesite plus quartz. And we fit those data with these curves. This is a very good fit, although there's no theoretical reason why they should be so beautifully symmetrical. But in any case, you see the temperature effect. This is the rate relative to the rate at 25 degrees C in air. So you can see the temperature effect with a peak rate at about 185 degrees C. And then you can see the effect of increasing the partial pressure of CO2 in these different curves from air to 70 bars. Beyond 70 bars, it really doesn't matter too much. So at least on a log scale. So you get this enormous acceleration potentially from temperature and pressure. And specifically, if we think about what can we get to go down a borehole where we have a 1 kilometer perforated interval that is accessing pore space over a 25 or a 250 meter radius. Depending on the temperature and the partial pressure of CO2, we can go from, and this is really what has determined the course of my research career for the last dozen years, 1 billion tons of CO2 per cubic kilometer rock per year, back of the envelope, to smaller rates if we access those rocks at lower temperature and lower partial pressures of CO2. So, you know, it's pretty easy in Oman, for example, to drill to a depth where the temperature is 50 degrees C. It's a little harder, but not terrible to drill to a place where the temperature is 100 degrees C. And as you go down, of course, you get pressure for free. And I'll just add that these uptake rates are not likely to be kinetically limited. So this uptake is basically limited by the amount of water that you can get to flow down a 13-inch pipe. Another thing that's kind of cool and important in all this is that there doesn't seem to be significant passivation in the system. So these are a bunch of data on olivine carbonation. And what's striking is that, first of all, that olivine in the presence of CO2-rich fluids at about, depends, but let's say 150 degrees C and a few tens of bars of CO2 partial pressure becomes 80% or more carbonated in a few hours. This is olivine, ground olivine with an average grain size of maybe about 50 microns. But the other thing that's really striking is that there's no evidence for formation of a passivation layer or a reaction rind on the outside of the olivine crystals. And why this is, we can talk about later if somebody wants to, but it's pretty cool. And it allows this very, very wonderful simplifying assumption that we can model this as a function of conversion at a constant rate. Okay, so engineered subsurface systems for storage of CO2, not removal from air, but storage of CO2. We can easily imagine just sort of accelerating the natural process that I've been discussing. The research on this was, I would say, greatly retarded by the existence of this diagram, which, as far as I know, first appeared in an IPCC report on CO2 capture and storage in 2005. And so what this diagram shows is that if I'm injecting CO2 into my favorite geological subsurface unit, the first thing I'm hoping for is structural trapping beneath a low permeability barrier. Then I'm imagining that CO2 is going to form bubbles in water in pore space, and so then it can't really move around very easily. And then it's going to gradually dissolve in the surrounding water in the pore space, and that's solubility trapping. And then when my great-great-grandchildren are having their great-grandchildren, then finally, carbon mineralization is going to make a difference. And so anybody looking at this diagram would say, don't waste my time studying carbon mineralization. And that is, in fact, exactly what a DOE program director told me when I started down this road. So this diagram has been reproduced all over the internet. It's everywhere. You can easily go find it. It turns out this diagram refers to a very specific sandstone in the Gulf of Mexico. All right, so in Iceland, people who were undaunted by that diagram decided to store CO2 emitted from this geothermal power plant that provides electricity for most of Reykjavik in what's known as the Carb Fix Experiment. So there's a geothermal power plant here. As you may know, when you condense geothermal steam, there's a lot of dissolved CO2 and also, in this case, hydrogen sulfide gas that is not condensable, and up until recently they were just emitting all that stuff into the air. So they now inject their CO2 emissions into these basaltic lavas, and they have production wells where they can monitor what's going on, and they kind of know the flow direction of the groundwater because they've been working there for decades. And so what they found was that for the 95% of the carbon that they inject in the injection well does not come out of the production well. So these black dots show what is expected based on carbon-14 as a tracer, and also based on, what's it called? Sulfur hexafluoride, SF6, as a tracer. And using both of these methods, about 95% of the injected carbon has been lost along the flow path by reaction with those mantle-derived lavas to form solid carbonate minerals. So if we then redraw that diagram from 2005, based on the knowledge we gained from Carb Fix, we first of all have to shift everything in order of magnitude to the left, and we end up with this diagram where mineral trapping will take care of a lot of the injected carbon in the space of a year or two. The other thing that's come out of Carb Fix, which is very valuable, is they say their operating cost for that CO2 storage process is somewhere in the neighborhood of $25 to $28 per ton. And if they had to build all the infrastructure that they don't build because there is a power plant there, it might be on the order of $50 a ton. The other thing I've noticed is, because they're Europeans or whatever, they're using this very, very high cost for electricity, $124 per megawatt hour. Industrial electricity in the United States costs half that much. And so these costs would significantly come down if they use this lower cost for electricity. Now, I've been talking about peridotite, and we briefly went off and talked about mantle-derived basaltic lavas at Carb Fix. And I'll just say that there's nothing wrong with basalts. Here's a agglomerate at the top of a basaltic lava flow, which has lots of porosity, and it has reacted over time with CO2-bearing fluids to form this white carbonate minerals. And so I would say that if I can find a glassy basalt, I'll be just as happy as a mantle peridotite. But going back to these kinetic data, here's dissolution rate data in moles per meter squared per second versus temperature. This big blue bar is olivine dissolution rates over many, many orders of magnitude. This pink area here summarizes the data for a variety of compositions of plagioclase feldspar, which is the most abundant mineral in crystalline basalts. And so you can see that above 75 degrees C or so, you're better off with olivine. And then here's, whoops, basaltic glass, maybe faster than olivine, certainly a good target. And here are alteration minerals. Serpentine is really pretty slow, but brucite, magnesium hydroxide, faster than olivine, up to maybe 150 degrees C or so. Okay, and then in addition, we're just fascinated by the fact that we can see all these beautiful natural products of peridotite carbonation on the surface. And if somebody can find me some outcrops like this in a basalt, I'll go study them. But meanwhile, let's stick with this. Okay, so a problem is that we can easily imagine negative feedbacks in this system. The reaction of water with and without CO2 with olivine forms serpentine and brucite and carbonate minerals, and all of those things involve an increase in the solid volume. And the porosity in fractured peridotite to begin with isn't that high, and so we can imagine that those reaction products are filling up the pore space, killing the permeability, and if that weren't bad enough, armoring the reactive surfaces so that reaction between the fluid and the remaining olivine is now mediated by slow diffusion through a solid reaction rind. Okay, so this is sort of standard metamorphic petrology. These kind of hydration, carbonation reactions are called retrograde because we don't like them, and they don't go very far because of these negative feedbacks. And yet, it turns out that completely hydrated peridotite, serpentinite, is very, very common, so much so that is the California state rock. And similarly, we can find places where peridotite has been carbonated to the point where every single calcium and magnesium atom has made friends with the CO2, and the silica that was in very silica poor olivine is now in quartz. So, and moreover, we know from, I showed you the carbon-14 data for Oman, but we also know for this very similar Lost City travertine deposit on the seafloor near the Mid-Atlantic Ridge, that these systems don't clog up, that they persist for tens of thousands, maybe hundreds of thousands of years in the same place. So somehow those negative feedbacks don't always apply. Okay, and so in order to explain the ubiquitous occurrence of serpentinites, Bill Fife, who otherwise wrote metamorphic textbooks about how retrograde metamorphism is self-limiting and never happens, came up with this idea that during serpentinization, there's a positive feedback that the big volume increase due to hydration creates stresses that break the rock, that cause fractures that maintain or even increase the permeability and expose new reactive surface area, and around you go until the rock is fully reacted. Here's a conceptual model from the group, the Physics of Geological Processes group in Oslo. So there's a blue rock here floating around in a black fluid. And when they react, they make this white stuff with a volume increase. The stresses due to the volume change make these red fractures. That provides ingress to the fluid. And gradually, the rock becomes completely replaced. And to my mind, although I would be happy to admit that textures don't really prove anything, to my mind, this picture here of a serpentinized peridotite with carbonate veins in it looks very, very much like basically this stage in that conceptual model. This process is also invoked in the oil field, as some of you may know. So Berg and Ganji calculated the stresses that are created in shales due to maturation of kerogen to form oil, right? So that involves a density decrease and a volume increase. And the proposition is that these stresses are sufficient to crack the rock, so that Lash and Engelder proposed that this creates the primary permeability in the Marcellus Shale, for example. So now I'm going to show you a movie of hydration of magnesium oxide to form magnesium hydroxide. I wish I was showing you a movie of magnesium oxide plus CO2 making magnesium carbonate, but we don't have that movie yet. But in any case, this reaction increases the solid volume a lot. So these clever people in Oslo found that you can purchase cylinders of ceramic magnesium oxide with porosities on the order of 10%. And they decided to run water through these cylinders from the bottom to the top inside an X-ray synchrotron to watch the reaction progress. And what is transparent in this slide is brucite, magnesium hydroxide, and what is orange in this slide is remaining magnesium oxide. And any of you who are familiar with thin sections of partially hydrated mantle peridotites are now nodding your head. This looks like relict olivine in a sea of serpentine. And this nearly complete reaction has been facilitated by the reaction-driven cracking process. I really, really hope my screen's not frozen. It is. Folks, this has happened to me a couple times recently, and there is basically nothing I can do about it except to shut down my computer and log back on. So in a minute, my voice will stop and my mouse will freeze. Let's just see if that has to happen. But I think we're doomed. Can you still hear me, Ben?
Yes, I can, but you're frozen video.
Yeah. Oh, the video's frozen?
Yep.
I think that indicates that this is fatal. Please stand by.
No problem.
Oh, yeah. Now I can't even see my mouse. Okay. Bye. good. No, I'm good. Hello, everybody. I'll take over again here, I think. Yeah. Okay, are we all set?
Good to go, Peter.
Okay, sorry about that. That has happened a few times recently. Where were we? Here. Okay, some of you may have already seen this pattern, but we often see these carbonate veins here with these orthogonal later fractures emanating from them, known on the drill site as Frankenstein cracks. And we're working on modeling the process that forms those with the idea that if we learn enough about the physics of this process, we might actually be able to dial it in when we're trying to do engineered subsurface carbon mineralization to find the conditions where there is reaction-driven cracking and a positive feedback, and avoid the conditions where the fractures clog up and everything comes to a screeching halt. In that context, I like to show this slide and just ask the oil geologists who were around in the room, wouldn't you like to have this fracture network in between your hydraulically induced cracks? So there might be reasons to understand this process that extend beyond carbon mineralization towards, for example, geothermal power production or extraction of evil oil and gas from tight formations. We currently have seismometers installed looking at microseismicity in an area that is actively undergoing hydration and carbonation, and to see if we can see the snap, crackle, and pop of reaction-driven cracking. And indeed, we see lots and lots of these little impulsive events that look like, tiny little bombs going off. And so I'm looking forward to the day when we can analyze these data. I am not 100% happy with the way my computer is. Okay, so let's go back to engineered subsurface systems for CO2 storage real quickly. The proposition is that we can drill and maybe stimulate a bit and drill another borehole to produce. And then we can move CO2 rich fluid through these rocks, heating and forming solid carbonate minerals as it goes, and then ask this hot carbon depleted water to return to the surface to take up CO2 from air or whatever. And this is just a geologist's cost estimate, not a real tectono-economic analysis, but putting together information from geothermal drilling projects that have been conducted by the DOE and industry in the United States over the past 40 years or so. I came up with a cost of about $10 per ton of CO2 stored by this process. So that's pretty competitive with other methods. Okay, here's a world map of places where one could consider doing this, with basaltic formations in purple and ultramafic formations in green. Here's the Oman Ophelite that we've been talking about quite a bit, and I've showed you lots of outcrop photos. One could go elsewhere to the Papuan Ophelite here in the Western Pacific, or the New Caledonia Ophelite out there in the middle of the ocean. Albania has quite an extensive network of those things. And in the United States, we're looking to California and southwestern Oregon as potential places for peridotite carbonation. And there's reasons why you might want to focus on those quite a bit, because this is also the site of active geothermal power generation. But if we really go for the best place in the world, here it is on the east-facing coast of the Gulf of Oman in the United Arab Emirates. where there is roughly 100 cubic kilometers of peridotite right on the seashore with ample water, 3 trillion tons of peridotite able to take up about 1.5 trillion tons of CO2 if it were completely carbonated. In addition, during the tectonic formation of those mountains and erosion, there have formed peridotite conglomerates offshore where the peridotite class surely have a higher surface area to volume ratio and constitute another good target for carbon mineralization. My colleagues would like for me to mention that one could also look at submarine basalts, which compose the seafloor under a thin veneer of sediments over most of the ocean basins as a potential storage target. And I know that Ben Tutelo and his students and postdocs are involved in a study for the potential of CO2 storage in basalts here offshore of Vancouver Island. Putting it all together, and if we let ourselves look offshore, the storage capacity in mafic and ultramafic rocks via carbon mineralization is hundreds to thousands of trillions of tons of CO2. Okay, let's move on to CO2 removal from air. I've actually excised a big part of this talk because I was worried about the time, but we'll do a little bit of it. So far we've talked about all sorts of different ways to use carbon mineralization. And the first idea that was really explored was to take peridotite, grind it up, move it thousands of kilometers to a power plant, put it in a high temperature pressure reactor, capture CO2 from a smokestack, and react them inside the reactor. And as you might expect, that was found to be quite expensive. It basically doubles the cost of the power plant. So leaving that option aside, one can use carbonation for CO2 storage, okay? And you could use mine tailings on the surface, existing tailings, or rock mined for the purpose of carbon capture and storage. And then we've talked quite a bit about how one might use the subsurface weathering system to store carbon. So now I want to segue into systems for carbon dioxide removal from air. And again, you can use crushed rock on the surface, either existing or stuff mined for the purpose. Or again, you might be able to design in situ systems where rather than circulating CO2 rich fluids, you're circulating ambient water in equilibrium with the atmosphere and stripping the carbon out of it. So I'll talk a lot about superficial carbon mineralization in a minute. I took out the section on subsurface carbon mineralization for CDR, except to put this little placeholder in here. It's pretty much the same idea as what we've already been talking about, except now we're using thermal convection. We've got an abundant source of water saturated in air. It goes down, it reacts, it heats up, it loses all its carbon, and carbon depleted water returns to the surface by thermal buoyancy to remove carbon dioxide directly from the air. That ends up looking a lot like a geothermal power plant here in this Wikipedia schematic. And indeed, there might be synergies between this kind of process and geothermal power generation. But what I want to do now is go off on a slightly different tangent and talk about superficial carbon mineralization for CO2 removal from air. And I want to do that because this is so simple and robust and kind of dumb that I think you'll see immediately that it might actually work and work pretty soon without a lot of questions. So this arose from an argument that I don't have time to discuss. But as grad student at Worcester Polytech working with Jen Wilcox, they've now moved to Penn, and I were arguing about how much it costs to produce CO2 by heating up limestone. So what we came up with, if you want to minimize those costs, is that you take calcite, or so calcium carbonate or magnesium carbonate, and you heat it up and drive off the CO2. and take the solid calcium oxide or magnesium oxide that you produce and just let it sit out in the weather. And lo and behold, these materials, calcium oxide, magnesium oxide, and their hydrates, are so reactive that within a couple of months, 75% of this material will be converted back into carbonates. Then we stick it back in this cooker. We take the CO2, we store it somewhere or use it for something and do it again and again. And because of this looping method, we drive down the costs of mining to produce this original feedstock and end up with a very simple process. So unlike what I've showed you for some other economic estimates, this is a real tectono-economic analysis. It may be wrong, but it's the best job we've been able to do. And so we figured out our energy costs for natural gas here using standard values for electricity and so on. We're going to lose 5% of our stuff per cycle. We're going to set out a layer for weathering that's 5 centimeters thick. And I'll show you in a minute that we think it will carbonate 75% in 2 months. Okay, that's pretty important. Here's our current best lab data. It's only 3 days long, but you'll see that the weight fraction calcium oxide consumed per second is not changing very much. This red line shows what happens if you just have an exhaustion model at a rate of 6 times 10 to the minus 7 mass fraction, 6 times 10 to the minus 7 per second. So actually the carbonation of the remaining calcium oxide in this experiment is speeding up. Anyway, these rates give us 75% conversion of calcium oxide to calcium carbonate in something like a month. And our cost analyses are, very scale dependent. But when we get up in the range of 10 million to 1 billion tons a year, they kind of show out at a relatively low cost. So per ton of CO2 net removed from air, $75 to $150 per ton. And because this process as modeled uses a gas-fired kiln and we capture the CO2 from the smokestack, we're also able to sell CO2 at a produced cost of about half that. So you can compare those numbers. That's the previous slide. There's all sorts of updating going on. This is happening in real time here. But anyway, so let's look at these numbers. But you can compare these to estimates for more highly engineered systems for removing CO2 from air using the same energy sources and cost assumptions. And you'll see that this is currently the least expensive method to remove CO2 from air, the least expensive peer-reviewed estimate of a method to remove CO2 from air in the literature. I also see that there's a thing here that's wrong, I'm sorry, but so based on our current lab data, if we have 5 centimeter layers and it takes 2 months to carbonate them 75%, we need a footprint of 2,000 square kilometers per billion tons of CO2 per year. And so how big is that? Well, it's about 1/7 of the size of the Nevada test site and the Nevada test and training range in southwestern Nevada in the United States. So that area, which is currently kind of a no-go for almost everyone because the Nevada test site is mildly radioactive and here they shoot lots of rockets, that area is sufficient, we think, to remove 7 billion tons of CO2 from air per year. That's 5.3% of the area of the state of Nevada, less than 1% of the area of the United States, and less than 100% of the global land area. If we can figure out how to fiddle with grain size and layer thickness and stirring and maybe add a little water and go twice as fast, then of course we reduce that area footprint. And so we're very enthusiastic about the potential for this particular carbon mineralization system to scale to billions of tons per year in the next 3 decades. So thank you for your attention. If you want to talk about subsurface carbon mineralization for CO2 removal from air, I've got a bunch of slides that I took out, but I see that I'm at my time or maybe a little over. And so for now, I will stop here. And thanks for your attention.
Thank you very much, Peter, for sharing that awesome research presentation. We're sorry about the technical glitches.
Well, it's
obviously
happened to me teaching a couple times recently, so I wasn't freaked out.
Right. Yeah, and I very much appreciate the simplicity of this technology and how it can be so easily explained. So I know that many of you probably have questions for Peter. Please type them into the Q&A box at the bottom of your screen. And please note that we today have enabled upvoting of questions that have already been asked in the Zoom chat. So if you like it, a question that's been asked, you really want it to be asked of Peter, please upvote it, and we can do that. So Peter, we'll start you off with a question here. If I can find my chat window, of course. Here's a good one, a good quick first one. Have you attempted any other dating methods on the carbonate veins other than carbon-14?
Yes, and it was a disaster. Okay, so you can read about it. First author is Evelyn Mervyn, who now works for Anglo American and did work for De Beers and initiated a carbon mineralization project for De Beers that some of you probably know, various Canadian folks involved in that. But in any case, so Evelyn tried the uranium decay series as a method for getting a handle on the time scale of carbonate vein formation in Oman. And it turned out that for whatever reasons, the uranium thorium ratio in the carbonate veins is very, very close to 1. And so for those of you who have thought about the uranium decay series, you'll quickly realize that that means that the thorium in those veins cannot be the daughter of uranium decay. And so it turns out that, okay, so you have to decide how much thorium was in the rock to begin with and what the initial thorium isotope ratio in that material was. And in the end, you can get whatever age you want by making the correct assumptions. So that's been disappointing. Emily Cooperdock, who it looked to me like some of you might be aware of Emily's work on uranium thorium helium dating of magnetite. She's gotten some dates out of magnetite bearing carbonate veins, but those are Miocene or maybe even Cretaceous veins that she dated. And so it hasn't shed a lot of light on the present day weathering process.
Great, thank you. So the next question posed by a faculty member in our department, Rajiv Nair. Can you explain why you only consider solid volume in the reaction-driven or hydration-driven cracker model during serpentization?
It's a good question.
Consider porosity? Yeah,
that's a great question. And in fact, if we don't explain that in grant proposals, we almost always get hammered. So in peridotite, whether they be unaltered crystalline rocks that are nice and pretty and green, or in serpentinites, the porosity never exceeds a few percent. And so in order to get enough water in there to fully hydrate the rock or get enough CO2 in there to fully carbonate the rock, you have to think in terms of an open system where fluid is flowing through that porosity of a few percent for a really long time, so that ultimately the integrated water rock ratio approaches values, in the order of 1. And so because we know that the porosity, the instantaneous porosity, is never very large, we don't really have to think too much about the fact that the hydration and carbonation reactions by consuming low density fluid actually thermodynamically have a negative volume change. And instead, we think of the porosity as being more or less constant or within a few percent. And the big volume change that matters is the increase in solid volume. And the increase in solid volume is ginormous because we're adding mass to the solid in the form of H2O and CO2. And we are also decreasing the density of the solid phases.
Great, thank you. The next question from Simone Puyati is it not counterintuitive to produce CO2 when the goal is to remove it?
Yeah, you obviously haven't drunk the Kool-Aid of the CO2 removal from air community. So I have a little catchphrase that I used in there where I said, we're going to take that produced CO2 and we're going to either store it permanently somewhere or use it. And so in the long run, we'd like to store that CO2 in the same way that you would store CO2 captured from smokestacks and other point sources of emissions. And frankly, although I'm a big fan of regionally appropriate carbon mineralization in peridotite for storage, I think most of that storage is going to be in the form of injection of dense supercritical CO2 into subsurface pore space. And I think that for a lot of reasons, but one is that oil companies already know how to do this and are injecting tens of millions of tons of CO2 into subsurface pore space every year. So in any case, so we'll store it in the long run. In the short run, as we try to get funds, and I'm working with several entrepreneurs for research and development and try and commercialize this because it will never scale unless it's commercialized. We look to people who might actually want to pay for CO2. And who are those people? Well, there's beverages and there's greenhouses and there's various chemicals where we now use urea as a carbon source. But the big one is enhanced oil recovery. And so a company based in British Columbia, Carbon Engineering, for example, that is focused on taking CO2 from air by a more engineered technique that costs more, frankly. But anyway, has a big contract or joint venture with Occidental Petroleum to take CO2 from air and use it for enhanced oil recovery. So in the short term, actually the entrepreneur that I'm working with most closely doesn't want to do that. And he thinks that Google and Microsoft and so on are going to pay for CO2 offsets for their emissions. And he'd rather go that way. And in that case, yeah, we would inject that CO2 into subsurface pore space for storage. But I'm not so sure. And so, and keep in mind, 60% of the CO2 that's injected for enhanced oil recovery stays in the ground. So you certainly aren't making carbon neutral fuel, but it's less carbon intensive fuel. That was
Great,
long, short question.
Yeah,
sorry.
It was a very good answer. Thank you. So the next question is from Fred Gallagher. Depending on the mineralogy of a tight shale reservoir, would CO2 create carbonate mineralization in a similar fashion? And would this potentially enhance fracturing of the shale?
Well, I think we have a patent application, or it might even be a patent that says so. It's a good question. I sometimes wonder if some of the enhanced production that people see from CO2 flooding in tight oil reservoirs might actually be just that. A little bit of reaction-driven cracking and permeability enhancement and not simply buoyancy force that they think it is. And it'd be really cool to try and instrument one of those CO2 flooding experiments independent of the fracking and see if you can hear it. There's a little bit of a sideline there, and it's surprising, but clay minerals actually tend to swell in the presence of CO2-rich fluids. And if you look at the volume changes involved in that swelling process, from the perspective of elastic strain and stress, they are huge percents of volumetric strain. And so I really wonder, you know, how is that accommodated in the subsurface? And it could be that there's a little bit of snapping and crackling and popping going on down there.
All right, I'm going to upvote a a lower on the rung question here, but I like it, so I'm going to ask it. What is your solution for the CO2 obtained for the calciner injection? What amount or volume are we talking about? I think this is give it to Sally.
Yeah, well,
type
it turns
answer.
out, so we were determined, this is upsetting to some people. So if you look at that techno-economic analysis paper, which by the way is now wrong in factors of 2, but fortunately it's wrong in a conservative direction. Anyhow, if you look at that techno-economic analysis paper, you'll see that our base model used methane to heat the calciner. And we used not just a totally standard methane fired kiln, but an oxyfired methane calciner. And, but it's a standard technology whose costs are known. And that's really was our goal, was not to go out on any technological limbs, unlike, I would say, most of the people in this business. In any case, so an oxyfired methane calciner really has only 2 gas species going up the smokestack, water and methane. Oh, sorry, water and CO2. And it's very easy with the temperature, right, to separate water from CO2. And so, yeah, we anticipate and have budgeted for nearly 100% capture of CO2 from the flue gas in that system. And that's why we have this funny cost, which isn't standard, the cost of CO2 produced. So in this case, we're asking, what is our break-even cost? If we take the CO2 we remove from air and we add the CO2 from the calciner smokestack, what is our break-even cost per ton of CO2 total? It's pretty low. And an interesting fact about that low cost is it's definitely in the range of the price that, for example, oil companies will pay for CO2 for enhanced oil recovery.
Excellent, thank you. So next question I would say is, how representative are the carbonation rates measured on the ground olivine, I guess, or brucite in some of those cases, when the permeability and porosity in natural peridotite are typically extremely low?
Good question. That's why, can we just like go and do this whole lecture again in 3 hours? This isn't, well, this is a fine diagram. Anyway, so that's why we use this y-axis, which is normalized to the rate at 25 degrees C in air. So we don't actually know the reactive surface area of the peridotite formations in Oman. But we do know roughly what the CO2 uptake rate is in that weathering environment in Oman. So instead of using the laboratory rates, we take the rate enhancement from the lab experiments and multiply that by the natural rate in Oman, and thereby hope to avoid some of the uncertainties that have to do with reactive, multi-scale reactive surface area in fractured crystalline rocks. Here's a better picture. And I'll be glad to continue with that if you want.
Yeah, that was a very eloquent answer to that question, which I'm sure you've been asked before.
Well, not that much, actually. I'm glad you asked, because we think we're very clever.
So my next question is from Randy Latoon. For potential subsurface projects, would you have any specific identified reactive deposits in Alberta or Saskatchewan? I know it seemed like on your plot there, you showed a lot of the intermontane region of BC having peridotite in it.
Yeah, I don't think I'm allowed to tell you where I went, but about a year and a bit ago, I went to one of Greg Dippel's favorite places in BC, and I was pretty excited about it as a potential pilot experiment site. It's a potential nickel mine with lots of brucite. And for one reason or another, my funders, who think of themselves as venture capitalists, were not able to come to an agreement with the mine concession holder. And there was also a lot of potential First Nation concerns that weren't really clear how they might be resolved. And so we have stopped that. As far as I know, we aren't proceeding with that at the moment, but there's quite a bit of tectonically exposed mantle peridotite and also some igneous rocks in the Tulamine complex, for example, that are suitable in BC. And I believe that in the not too distant future, one might expect to see a survey of those potential rocks coming out.
Great. Thank you for that one. So another question is there a way to remove CO2 from the air to produce carbon mineralization in the truest sense? And I think that's sort of what the first part of your talk was about. So,
well, we could do it once. We could take the calcium carbonate. I mean, this is basically the same as adding alkalinity to the ocean. We could take the calcium carbonate, we could cook it, we could make calcium oxide, we could take CO2 out of air, and then we could just leave it there. But there's two reasons to cycle it, as I described. And one is that you drive down the cost of your feedstock with every cycle per ton of CO2 removed from air. And the other is that you make a much smaller mess if you reuse that feedstock over and over again, rather than letting carbonated tailings sort of pile up in your backyard. And if you want to look, I think there's a chemical geology paper in 2020 that a group of us published, and there's also the National Academy report. And both of those, I used various yardsticks for how much tailings might pile up for a one-time mineral carbonation, surficial mineral carbonation system. And my favorite yardstick is, how deep would you make a pile of carbonated tailings in the area of Washington, D.C.? It's pretty deep.
Thank you very much for that answer. So the next question that's been upvoted to the top here is, the ability of inexpensive CO2 storage is already seen by fossil fuel producers as the license to extract and use more fossil fuels, so sort of a greenwashing idea. CCS represents something new for the world in that we are taking over the management of the carbon cycle from natural systems, I guess the equivalent of intubating and ventilating a person, as this person says.
Wow.
Do we need to consider the future path dependence that we are creating?
Well, I hear that a lot. And while I look for my slide, I'll just say that at least in the past, Greta Thunberg and the Sunshine Coalition do not approve of what I have been telling you about, because they view it as a get out of jail free card for their enemies, the fossil fuel producers. However, I have two responses to that. One is that pretty authoritative sources, I mean, first of all, there's an enormous amount of uncertainty in this slide that isn't shown, right? There's no error bars on anything. So we don't really know exactly how the climate is going to respond to CO2 injection and methane injection into the atmosphere. And we don't actually know what the economic damages of that are going to be. So this is all very approximate, but I do have confidence that the IPCC and the other groups that make these projections are doing the best job they know how. And they have concluded that after or as you do all the point source capture that you possibly can in this green area on this graph, there are still recalcitrant greenhouse gas emissions of CO2 for air travel, for example, plus cow burps and stuff that are much harder to control. And therefore, if your goal is to maintain a sustainable climate, you have to engage in negative emissions, and quite a lot by mid-century. So if the Sunshine Coalition doesn't believe that, I'd like to see their alternative model. The other thing I would say is that from my perspective, it is probably a mistake to demonize the oil and gas industry. If we want to move tens of billions of tons of fluid around on the surface of the planet and put it underground in the next 30 years, The people, I can sit and talk about it, and I can even make some cost estimates. But the people who know how to do that are the oil and gas industry. We need their expertise. We need their participation. And moreover, if you just stop oil and gas by fiat tomorrow, you're going to disenfranchise a giant proportion of the contemporary economy of the planet. So if we can persuade those people to come with us and work with this, then there's many, many advantages to be found.
Great. So we have time for just a couple more questions. So I like this one from Duncan Berry. Does the geology and chemistry require CO2 saturated in water as the delivery media, or could you inject a high purity liquid or supercritical? Or
you could. So
CO2
yeah, let's go back. There's so many branches in this tree now. Certainly in this domain, you'd want to use supercritical CO2. And for the in situ injection for storage, not CDR, but storage, you might well want to use supercritical CO2. In particular, because the compression costs get multiplied or, well, divided by the concentration of CO2. So if you have an aqueous fluid with 100 or 1,000 ppm CO2 dissolved in it, and you spend a penny to pump some mass of that fluid, that turns into $10 to $100 per ton of CO2 per equivalent weight of CO2. So there's lots of reasons why you might consider using damp supercritical CO2 for in situ storage. It'd be hard to use it on the surface. So for tailings, we're pretty much stuck with ambient fluid. But for underground storage and reaction, you know, I'm just a humble igneous petrologist, and I think that damp supercritical CO2 and CO2 saturated water are exactly the same thing from the perspective of chemical potential. And so I don't think the rates are going to be that different, but there's definitely some advantages to moving it around as a CO2 enriched fluid. On the other hand, for CO2, for carbon dioxide removal from air, well, you're stuck with water saturated in air.
All right, I think we're going to ask 2 or 3 more questions here. Rajiv Nair asks, is the carbonate growth in the natural and experimental systems epitaxial? In other words, do you need carbonate there to nucleate new carbonate?
No, certainly not in experiments. Might be a little hard to find out by interrogating a natural rock, but in experiments, we get, you know, we could start pure olivine and get plenty carbonate. There is a little thing in there, though, that's interesting. And that is that some experiments, flow-through experiments that used sintered aggregates of minerals have yielded surprisingly low rates. And I don't know, but I think what happens is that if you decide you're going to sinter your starting material at 1200 degrees C, let's say, and hot press it, you bake out all the defects in the olivine, and you probably also bake out little things like a little bit of brucite here and a little bit of serpentine there that could form fast reacting nucleation sites for the carbonate. So in the experiments we're starting now, we're doing everything we can to avoid hot pressing our starting material.
All right, so the next question is, I think, so you mentioned purchasing carbon credits from Microsoft. Could the captured CO2 be put towards the refrigeration processes for cooling servers, et cetera, and reduce cooling infrastructure and reduce global warming in the same process?
I don't know. That's a good engineering question. I kind of suspect that there might be fluids much better for refrigeration than CO2. And so you might be better off burying the CO2 and using the other fluid, but I don't know. That's a good question.
All right. So second to last question, the cycling system that you present with the McQueen et al. Paper is not unlike carbon engineering's technology in a way, right? Where the contactor and some other bits has been replaced with distribution recollection of the sorbent. in your techno-economic modeling, is the driver of the lower levelized costs in the CapEx or the OpEx? I'm not sure I'm saying those words right.
CapEx and OpEx. Both. We don't have, although the engineers I work with are constantly inching back towards more complicated systems, and I'm like, no, the whole purpose of this is to be simple and dumb. But anyway, in the base model, we don't have elaborate contactors. And that, along with some multi-step chemistry in the carbon engineering process, that is the big difference. So an engineer thinks, I've got to maximize the surface area of my sorbent, and I have to maximize airflow past my sorbent in order to do something in a few minutes or hours, because it costs me so damn much to build the contactor and all that stuff. So we don't build that, and it turns out maybe it's quite a bit cheaper not to build all that infrastructure to begin with. The second point is that they spend a lot of money getting the sorbent off the contactor. And we don't really have that problem. You could probably use a front loader to pick up the carbonated material. So although I don't know in detail exactly all the points where we come out a little less than Dave Keith's paper in Joule, I'm confident that we do, at least for now. And keep in mind that the published cost estimates for more highly engineered direct air capture systems, everyone agrees it's currently quite expensive, might be $400 per ton. And so the numbers you read, and I would direct you to a table in chapter 5 in the National Academy report, which I think is authoritative and peer reviewed. Nonetheless, the numbers you read are projected future costs that incorporate assumptions about improved technology in the future and economies of scale. And so in that way, when you compare that to the cost estimates in the McQueen et al. Paper, it's a little bit apples and oranges, because all the costs in the McQueen et al. Paper are current costs for demonstrated technology.
All right, Peter, last question. Do you think these natural or even engineered environmental carbon sequestration systems where it's passively occurring will become more of a dominant role in sequestering carbon versus these big injection plants or geothermal plants for carbon sequestration?
It just really depends on what people want to do. This idea that I talked about in the last 15 or 10 slides here requires a population that is prepared to assume the cost of covering thousands of square kilometers with ground up rock for the benefit of low cost removal of CO2 from air. And I can't really foresee how that's going to come out. So there's a guy named Larry Linden who works a lot on carbon mitigation policy, super nice guy. And I said to him that I thought this probably won't happen in the United States because there's large groups that really, really value our open space, no matter how monotonous. And so I thought, well, you know, maybe Saudi or Western China. And it was Larry who said, well, I don't know, what about the Nevada test site? I was like, okay, that's going into the paper. But you know, that it's those kind of decisions. Right now, my perception, just to get on the wrong side of everyone listening here, my perception is that the sort of conventional advocacy-oriented environmental movement in the United States is at a point where they simply won't accept any negative impacts for any mitigation technology. They're not interested in cost benefit. They just won't accept any costs. And if we continue down that road, we're not going to do anything, because moving 10 billion tons of fluid around on the surface of the Earth is not going to be pretty. It's 2.5 times as much fluid as the oil and gas industry moves around on the surface of the planet. So if you want to manage greenhouse gases at the gigaton scale, you have to be prepared to accept some environmental impacts.
Excellent. Thank you very much. So a special thank you to Dr. Peter Kelvin for being part of this year's virtual Tom Oliver lecture series. I'd also like to extend a thank you to the Oliver family for supporting this annual event and for joining us this afternoon. As mentioned earlier, this annual lecture series gives the Department of Geoscience and the Faculty of Science at the University of Calgary the opportunity to welcome world-class researchers such as Peter to our community. Our students, faculty, staff, and alumni and community members continue to be enriched by learning from our series speakers. If you're interested in supporting our research or any other faculty initiatives, please visit the Faculty of Science website at science.ucalgary.ca. I'd like to remind you that our Gallagher Colloquium series resumes in January 2021 with a presentation from Dr. Susan Brantley, who is joining us from Penn State University. Dr. Brantley will discuss how fracking affects our water. Look for registration details in your inbox, or by checking out our website at science.ucalgary.ca. Again, thank you all very much for spending your afternoon with us. Have a great rest of your day, and we will see you all soon. Bye.
Let me just say thank you to everyone for your patience with this long talk, and I enjoyed the discussion a lot.